What are the challenges of debugging quantum programs? Imagine trying to fix a puzzle where the pieces can be in multiple places at once, and you can't see some of the pieces directly. That's what debugging quantum programs feels like. Quantum programs run on qubits, which can exist in superposition and become entangled with each other. Because of the no-cloning theorem, you cannot copy or directly observe the state of a qubit without changing it. This makes inspecting the intermediate steps of a quantum program very tricky. You can't just pause and look at the data like in regular software. Instead, you have to rely on indirect methods, which can be less precise. Another challenge comes from the probabilistic nature of quantum computing. Instead of getting a clear answer, quantum programs give you a distribution of possible results. If there is a bug, it might show up as a small deviation in these distributions. Detecting such tiny differences requires many repeated runs and careful statistical analysis. This makes debugging slower and more complex than with classical programs, where errors are usually obvious and consistent. Quantum bugs often happen because of mistakes in the sequence of quantum gates, errors in handling measurements, or logical errors in hybrid quantum classical algorithms. Fixing these bugs demands a good understanding of quantum mechanics and how quantum programming languages work. It's not enough to just look at code. You need to understand the physics behind it. Current quantum hardware also adds to the difficulty. Noise and hardware imperfections can cause errors that look like bugs but are actually caused by hardware issues. Differentiating between a software mistake and hardware noise is hard, especially since quantum devices are still in early stages and prone to decoherence and other noise effects. Debugging tools for quantum programs are still developing. Unlike classical debugging, which has well-established techniques, quantum debugging needs new approaches. Some methods involve assertion-based debugging, mutation testing, or statistical checks, but these are not yet mature or widely available. This means developers often have to create custom solutions for their specific problems. As quantum programs grow larger, debugging becomes even more challenging. More qubits and complex circuits mean more possible errors and a bigger state space to analyze. Finding bugs in such large systems is an ongoing research area. To tackle these issues, developers use simulators that give full access to the quantum state, helping visualize how the program evolves. They also run many tests to compare actual results with theoretical expectations. Some tools allow partial measurements during execution, which can help identify errors without collapsing the entire quantum state. Dividing large circuits into smaller parts for targeted testing is another strategy. Overall, debugging quantum programs is a mix of understanding quantum physics, developing new tools, and applying clever testing strategies. As the field advances, improving debugging support will be key to building reliable quantum software.